Hello and welcome to this lesson on designing for thermal comfort in buildings. The content of this lesson are the role of HVAC systems in thermal comfort, the key design considerations for HVAC systems, and designing for thermal comfort. So the learning objectives are understand the key factors influencing thermal comfort in buildings, discuss the role of HVAC systems to maintaining thermal comfort, and identifying strategies for designing comfortable environments. So let's start with a question. How can we design buildings that are comfortable? We have talked about in previous lessons about how different people have different preference for their thermal comfort. So for example, we have talked about the difference between the metabolic rate of people and the difference in clothing and how this affect to the thermal comfort. So in this lesson we're going to learn how we can create environments that satisfy at least the 90% of occupants in a building. So the role of HVAC systems in thermal comfort is that thermal comfort is influenced by air temperature, humidity, air velocity, and radiant temperature. And with HVAC systems, the most important two parameters that we are going to control are the air temperature and the air velocity. From these parameters, we researchers have developed different equations based on empirical and laboratory evidence. And for example, here for the optimal skin temperature, this relationship shows the temperature in relationship with the metabolic rate and the work that is done for a person. So here we see that the highest the metabolic rate, it means the harder activity that the person does, then that optimal skin temperature is going to be lower. So we were going to need colder indoor environments. But then we also know that there is a optimal sweating rate. So this means that is the energy that we lose by our sweat. And then the higher is the metabolic rate, then the higher this optimal energy sweating rate is. But this sweating rate, so the rate that the person is going to evaporate as sweat, it also depends of the temperature of the room. And then the optimal air temperature. For example, in this case, for a humidity of 50%, air velocity lower than 0.15 meters per second, and the light activity, we have that the optimal air temperature is going to be given by this relationship that depends of the clothing resistance of the person. So in this graph, we can see here plotted the same relationship where we see this is the optimal temperature that we just presented, and here are draw also the upper and the lower limits to create a environment that satisfies 90% of the occupants. So we see this that as this relationship depends on the clothing insulation, so the higher the clothing insulation for light activity, then the lower there is going to be the optimal comfort temperature. And then we can see that people dressing in two different ways, like with a summer dress with 0.4 or with a suit around 1 kilo. So we see the difference can be on optimal temperature can be on 3 or 4 degrees. Here is a plot of the same optimal air temperature, but in this case is given also depending of the activity levels. So we know that the higher the activity level, then the higher the metabolism, and then our optimal temperature needs to be lower. So we see here that for activity level, at the same clothing, the temperature, the optimal air temperature is going to be lower with lower activity level. But then we also see how the impact of the clothing thermal resistance. So the same activity level, we are going to need different optimal air temperatures according to how we dress. So because of this difference between the people that is inside a room, so they're going to prefer different optimal temperatures. When we design an HVAC system, we talk about zones. So we talk about a thermal comfort zone that is recommended by the SRAE, where this is a zone where most people are going to feel comfortable in an office. So this is the key design consideration for HVAC systems. Here is the optimal zone for winter and for summer. So in winter we assume an average clothing of 1 kilo, and for summer 0.5. And then this zone is going to depend on the temperature and the humidity ratio of the air. And then we can see here that these parallel lines that are drawn are lines of equivalent effective temperature. So effective temperature is the temperature of air that will give the same total heat loss as occurs at 50% of relative humidity. So we also see that the temperature ranges for winter are between 20 degrees and 25 degrees, and for summer between 24 and 28 degrees. And then the humidity is going to be more or less the relative humidity that is plotted in this part is going to be between 20% and 80%. So a humidity rate above 80% is uncomfortable for the people because the skin feels too damp. But it is also recommended to keep it just at 60%. And then at lower than 20% is uncomfortable for the people because it's too dry, especially with the humidity radius below 0.044 kilogram. Finally, we're talking about designing for thermal comfort. There is another important definition, that is the operative temperature. So operative temperature is the temperature of air that will give the same total heat loss as occurs when there is radiation of surfaces at a temperature different from the air temperature. So the operative temperature considers both the effects of the radiant surfaces and the air temperature. And it could be appropriate to use the operative temperature in cases where the surfaces have a very different temperature than the air. For example, during winter, if the windows are colder than the indoor air. But in most cases, just controlling for the air temperature is good enough to create comfortable environments. Then the air velocity also needs to be maintained between a range of 0.1 and 0.6 meters per second. Lower velocities than this range will create an environment that it could feel too stuffy, and over this range it could create drafts that are uncomfortable. Then there are also individual variations that between the people that affect their preference. For example, due to factors like age. When people is aging, the metabolic rate decreases for the same activity. Thus, the older people prefer higher comfortable temperature than younger people. Then there is also the effect of acclimatization. So people can adapt to different thermal environments over time, but their preferred comfort levels will remain stable. But even though these differences, we are recommended to use the SRI comfort standards that provide guidelines for designing HVAC systems that will ensure comfort and satisfaction. So, there are key takeaways from this lesson. We have the HVAC system play a crucial role in maintaining thermal comfort. So understanding the factors influencing thermal comfort is essential for effective building design. And by carefully considering design factors and implementing appropriate strategies, we can create comfortable buildings. I invite you to continue learning about thermal comfort with other lessons like thermal comfort in special environments, like environments like hospitals, the impact of indoor air quality on thermal comfort, like the impact of air pollution, and advanced HVAC control strategies to keep comfortable environments and optimize the energy efficiency. So thank you for listening to this lesson.